Okay, good afternoon. So I'm going to take you a little closer to Earth and describe you the work that we do on blue waters. So first of all, let me acknowledge my collaborators. A partial list is here. Funding comes from NASA and NSF. The problem that we are solving is related to kind of detailed physics of plasma turbulence. And we think it's an interesting problem that has universal applications because plasmas are universal, and turbulence is probably encountered in all kinds of systems, from laboratory fusion reactors to the sun, to the solar wind, the planetary magnetospheres, heliosphere, and astrophysical objects as well. And the type of turbulence that we are interested in is, first of all, it's a plasma turbulence, not hydrodynamic turbulence. And second, it's characterized by universal behavior of a large range of scales. An example is shown here. This is density fluctuations in the local interstellar medium, and you can see there's something like 12 orders of magnitude in scales over which there is a single power law. We're not trying to solve all the problems in plasma turbulence. We're focusing specifically on the turbulence in the solar wind. And solar wind is a stream of plasma that is emitted by the sun with variable speed. So a picture on the left is observation of solar wind speed at a particular moment in time. And the figure on the right is a spectrum of magnetic fluctuations in the solar wind. It's a composite spectrum taken by multiple spacecraft and multiple instruments on multiple spacecraft. And you can see there, it looks very much like your cartoon picture of turbulence. There are several characteristic ranges of scales over which there is a universal behavior, probably signified by presence of the power laws. At very large scales, the energy is still injected into the system, so we call this the energy injection scale. There is a large range of scale where it looks very much like inertial range of fluid turbulence. And then finally, at small scales, the physics changes and the nature of the fluctuations changes. And probably this is where the energy of the fluctuating energy is finally dissipated. And it is precisely this range of scales that we are interested in. And the reason is that unlike what happens in fluids, the dissipation of energy in hot collisionless plasmas is a complicated process. It's not just due to binary collisions, it's due to collective wave-particle interactions. From the practical point of view, the dissipation of energy serves as a local energy source in the solar wind and the solar corona. And so there are many unsolved problems regarding the global structure of the system that often people invoke turbulence as this local source of energy, but details are important for understanding things like where the energy goes. Does it go to energetic particles, into electrons, into ions, into minority ions, etc. So there's a lot of excitement in heliophysics community thanks to the upcoming launch, actually this year, of two missions. One is the NASA mission called Parker Solar Probe. The other one is a European mission called Solar Orbiter. And both of those are expected to really revolutionize our understanding of the sun, the solar wind, maybe the solar corona. In particular, the Parker Solar Probe will make really close passes, coming as close as 10 solar radii and taking in situ data in these regions. So this will provide really unprecedented data. And of course, we need theory numerical tools that are capable of handling plasma under those conditions and that can provide predictions and maybe help interpret the observations. So from the point of view of turbulence, one of the things that happens is that we expect that the nature of fluctuations in this short wavelengths range of scales is going to change. And that is because if you move closer to the sun, the magnetic field begins to dominate. So we usually talk in plasma physics about this parameter beta, the ratio of thermal pressure to the magnetic field energy density. And the figure on the left is a prediction of a particular model for the global structure of the solar wind that tells us that the plasma beta is expected to drop closer to the sun, meaning that the plasma is becoming more and more magnetically dominated. And moreover, the beta for different species for electron and ions is not dropping at the same rate. So the electron beta is dropping faster. This is the red curve. Ions are is not dropping as fast. And so there is a theoretical prediction from several groups that this change in the parameter beta is expected to result in a change of the origin of the nature of the fluctuation at short scales. And this is kind of shown symbolically here. So kinetic Alfvén regime is what we have at 1AU. This is the regime of turbulence that is relatively well studied. There are still a lot of unsolved problems, but there are lots of in situ measurements and theory and numerical simulations targeting this particular regime. But in low beta regimes, a new kind of window opens for fluctuations, and it's often referred to as the inertial kinetic Alfvén regime. There is certain relation between the two, but they're different. And that change in the nature of fluctuation is expected to result in the change in the dissipation mechanisms, structure formation, a lot of other things that we are interested in. From the numerical point of view, as plasma beta becomes lower, the various internal scales in plasma separate from each other. So something like gyro radius may become much smaller than the inertial lengths. And so that means that it's a very challenging regime for any kind of numerical method, because not only we need to now resolve the separation of scales from kind of macro to internal length scales, but we also have sufficient separation of scales between the internal scale lengths. So it's a difficult problem. So what kind of methods can we use to solve it? Thankfully, there is a kind of a single governing equation that we believe describes plasmas in these regimes at least sufficiently well, and that is the Vlasov-Boltzmann equation coupled to the system of Maxwell's equations. The problem with this is that it's a 6-dimensional PDE, and for that reason it's really difficult to solve. There are many approximations that have been developed in plasma physics over many decades, and they usually kind of analytically integrate certain degrees of freedom in this equation, yielding reduced models. But for some problems, like the problem that we're interested in, these microscopic processes that live on small kinetic scales actually are expected to influence dynamics at large scales, and therefore they require a solution of this equation, at least in an approximate fashion. So our go-to model for a long time has been particle and cell simulations. Again, we solve this equation using Lagrangian markers that represent a fraction of phase space, and electromagnetic field lives on the grid. There is a constant interpolation back and forth. And I'm not going to be talking too much about it. The important thing is that the particle and cell method is a very efficient, very scalable, very robust method, but it's also relatively inaccurate. And this is a problem for us because we want to study at the very end of the cascade where the fluctuations are very small. And even though they're small, they're just as important as large scales, because the energy flux through these scales could be exactly equal to the energy flux through the large scales in principle. But the fluctuations are small, and so that poses the challenges. So what I wanted to talk in today is a development of a new tool that in principle at least is well suited for this type of problems. And so it's called the Spectral Plasma Solver, simulation tool for fluid kinetic coupling. So our goal is a higher accuracy implicit fully kinetic simulation. So we want to solve the kinetic equations. The problem is it's 6D, so if we cannot just simply grid the phase space. If you imagine that you do a modest resolution of something like 100 points in each direction, you already end up with 10 to the 12 unknowns. That's hard, probably impossible for an implicit method. And one of the solutions to this problem could be an efficient discretization of the velocity space. So we believe that at least 3 out of 6 dimensions can be discretized in an efficient manner. And that is because, at least globally, sometimes plasmas have distribution functions that are not too far from Maxwellians. And that suggests some kind of expansion in terms of the Hermite basis functions, so Hermite polynomials times a Gaussian. So you can describe Maxwellian with one coefficient, right? Adding more coefficients allows you to describe more and more complex distribution functions, and therefore, in principle, catch more and more kinetic physics. It could be done in an automated way, thanks to the recursion relation between the Hermite polynomials. And it also opens up a very attractive possibility of kind of adaptivity in this 6-dimensional space. So it would really allow us to do adaptive physics in some sense. So the idea is by no means new. It was proposed in the 60s. Many papers that are not listed here. But in the last decade, people are starting to kind of try to move this from 1D toy models to production simulation code. And this is what I'm going to discuss today, the application of this method to turbulence problem. The method that we're using was proposed by my friend and collaborator Gianluca Delzana in 2015. So the current implementation is a Fortran 90 code. We use fully implicit time discretization to allow us to step over scales that we believe are not important for the particular problem. We solve the resulting nonlinear equation using PETSI. It's a Fourier in space, so we need to have a parallel FFT library, and the underlying FFTs are taken using the FFTW MKL. So here is a scaling of the code on blue waters, very, I think, typical for this type of code. So on the left-hand side is a single convolution, which is by far the most expensive operation that we do in the code. And on the right is a complete cycle. And this deviation from ideal is, of course, when communication starts dominating. However, we are not too perturbed by this yet, because we have a 6-dimensional space, and we've split FFT over just 2 out of 6 dimensions. So there is a lot of parallelism left to explore, and hopefully that will help us quite a bit. So, okay. Very quickly, some applications to turbulence. So this is a benchmark, and not so much of the code itself as the benchmark of the method. We are solving a linearized problem, and we're describing collisionless damping of certain modes in plasma, actually of kinetic Alven modes. For linearized problem, we can get a kind of quote-unquote exact solution, meaning it's numerical, but it's very accurate. And the points are the SPS simulation. So with something like 6 coefficients per direction, we can reproduce collisionless damping of different modes in plasma. And this is actually very fascinating if you think about it a little bit deeper. And that's because the collisionless damping is a very subtle physical phenomenon. Just as a point of reference, 2010 Fields Medal went to kind of a rigorous mathematical explanation of Landau damping. Here's another test. So this is a relatively small simulation of decaying turbulence. We can get a reference solution with the peak method, particle and cell. This is the black line, and the red and blue are SPS simulations. So the top figure is the spectrum of magnetic fluctuations. So this is a quantity called magnetic compressibility. It's a ratio between different components of magnetic field fluctuations. It's kind of like a fingerprint of the simulation, of the fluctuations. It tells us what the origin of them is. And there is a little bit of a shift in the curves, but that's just due to overall normalization, so nothing too worrisome. And finally, this is, again, still relatively small, but a simulation of decaying turbulence in this low beta plasma, so this regime that we expect to happen close to the sun. This is already the problem that we cannot do with traditional methods, at least not without spending all of our allocation on it. And a good thing here is that there's, for certain things like spectral slopes, there is a theoretical predictions, and this we seem to be able to reproduce, or at least be consistent with these theoretical predictions. The middle panel is, again, this signature of the fluctuations, magnetic compressibility, and this is kind of a normalized density fluctuations. So eventually, we hope to be to use this method to go kind of beyond simply confirming theory, and that requires much larger simulations. So we can do something like this in 2D. This simulation shows still the old method, the particle and cell simulations, and it kind of associates the structures in turbulence, these current sheets, the regions where magnetic field is highly sheared, with production or generation of energetic particles. So this middle plot is a kind of combined density in the tail of the distribution, and you see that this is indeed associated with the current sheets. So here's my summary. I guess I'll let you read and